Okay, well, I think we'll get started. It's nice to see our friends from G&G here and from across campus. It's a real pleasure to introduce Ellen Mosley Thompson today to FES. Ellen is a distinguished university professor. I almost called you the president. Maybe that's just a little slip there. In the Department of Geography in the Atmospheric Sciences program at Ohio State. She's also the director of the Bird, Polar, and Climate Research Center at the university. She's a glaciologist, a climatologist. She's done amazing pioneering work on ice cores. She's really one of the pioneers in climate science, reconstructing Earth's long history using ice cores. She has led 16 expeditions to Greenland, to Antarctica, but she's worked all around the world, including in Peru, Bolivia, Tibet, in the Himalaya. She has been PI or co-PI on 51 federally funded research grants. She's very busy. From NSF, from NASA, from NOAA, when you look at the programs and projects that she's led, they're these really big research programs to conduct the research that she's doing in these places. When you look to see the list of places and societies that she's been a member of, it reads, well, it's a very long list, let's just say. She's an elected member of the National Academy of Sciences. She's an elected member of the American Academy of Arts and Sciences, an elected member of the American Philosophical Society, an elected fellow of the American Association for the Advancement of Science, an elected fellow of the American Geophysical Union. She's the recipient of a number of scientific awards and prizes, including the Benjamin Franklin Medal. And not only is she conducting amazing research, she also, in her spare time, she is currently the AGU Focus Group President for the Global Environmental Change Group. So a number of us hear from Ellen regularly getting notices about that. She also served on the NRC committee that produced the report, The Arctic in the Anthropocene, Emerging Research Questions. And I just learned that she and Tom Gradle last century were co-chair of an AGU group together. And I think that Ellen is the only person that we have had come speak who has a cirque named after her in Antarctica for her pioneering work there. Her undergraduate is in physics from Marshall College. She's from West Virginia. She went to Ohio State to get a master's degree in geography. She stayed on at Ohio State to do a PhD in geography, and she's been there ever since. Please join me in welcoming Ellen.
Thank you. I have to turn this on. Is it on now? Have I done it correctly? Can you hear me? Okay, great. All right. Well, thanks everyone for coming. Appreciate it. I guess I'll just get started. I have a few comments, but I'll make them as I go along. So I want to start with this image because it shows the type, I guess you could say this shows our laboratory. These are some of the places where we've drilled ice cores. Bruce Plateau in the Antarctic Peninsula, Desapu, very high, 22,000 feet elevation ice field in the Himalaya, and Crawford Point in Greenland. And as Karen was reading off some of the awards and et cetera, it's really important to realize that very few scientists do their work in isolation. And in fact, the work that I'll be presenting is the collective effort of our team. Of course, Lonnie Thompson and I, as fresh PhDs, started the Ice Core Paleoclimate Research Group at Ohio State, and we've been conducting that research for almost 40 years. But we have a team of professional scientists. We have 4 postdocs right now and 2 graduate students. And our funding comes primarily from NSF, NASA, and NOAA. So I say thank you to my team for doing such wonderful work, and to Lonnie as a partner in that. So I'm going to start with just a few slides about climate, because Karen said that everyone here is experts on that, and I'm going to get right into the ice core part. So we know that the Earth is warming and that environmental conditions are changing. We can look at the global land ocean temperature from 1880 up to 2016. And this shows, these are the annual values, the dots. But when we look at the spatial distribution of the trends, it becomes obvious that the Earth is warming almost everywhere, but not quite everywhere. There's a place in the North Atlantic where the trend has been negative. And there are many places where there's insufficient data to actually go into the global database. 2016 was the warmest year on record, it exceeded 2015. The prior warmest year was 2014, then 2010, 2005. And since this record began in 1880, the globally average temperature of the planet has warmed about 1 degree centigrade, or 1.8 degrees Fahrenheit. And just to put that into perspective, it's estimated from paleoclimate records that the temperature difference between today and if we want to go back about 18,000 years when the Earth was in a glacial stage, in Columbus, Ohio, where I live, was under a mile of ice, that temperature difference is just 5 or 6 degrees centigrade. In the different direction, now we're 1 degree warmer. So 1 degree might not, for a global average, might not sound so big, but when you look at it from a global perspective and from an historical perspective, it's quite large. And the climate of the last 40 years has been remarkable. We've had this increased frequency and intensity of extreme weather. We've had heat waves in Western and Central Europe with tens of thousands of deaths, in Eastern Europe and Russia, and also fires and smoke contribute to death. We've had prolonged droughts, and along with droughts, we get more fire, and we've had large floods. And the Intergovernmental Panel on Climate Change, the IPCC, their models predict that these type of responses to global climate change will become more frequent. And you'll see more of that in your future than I will, quite likely. So I just showed you the 120-year record. We need a much longer record to put what I call the contemporary records into a perspective that's important for evaluation of the current changes. And we can reconstruct Earth's climate history using these paleoproxy indicators, ice cores, tree rings, corals, the ocean and lake sediments, and from the lake sediments we get pollen histories, and also the speleothems provide these histories. But today I'm going to focus just on the ice cores. So as I go through the talk, it's going to focus on two big themes, and that is what we can learn from ice cores, and the fact that glaciers around the world are essentially melting, and as they melt, we're losing the records. I'll show you some examples of that. We're losing opportunities to collect more records. Also, ice plays an important role in the Earth system, and as I go through the talk, be thinking about the fact that ice records changes, thus provides these paleo records, but ice also is a driver in the climate system. It can force changes, and ice responds to change. We'll see examples of all of these. But first, I'd like to just give you a little bit of history and background information. Karen mentioned that you might be interested in just a little bit about some of the expeditions. So my first trip to Antarctica was in 1982, and I had the opportunity to join an international team to drill ice cores at South Pole Station. So just to show you and I just want to point out, so here we're in the C-130 aircraft flying up to South Pole. We're flying over the Transantarctic Mountains, coming up on the polar plateau. These mountains look small, but they're actually very tall, but they're bathed in this big ice sheet. And this is the C-130 aircraft that we typically and still use in Antarctica. This is the South Pole Station as it appeared when I was there. It was built in 1974. It's gone. They've put in a nice new station. But at that time, most all of the living activity was under this geodesic dome. Not much fanfare, but the year I was there, that is the South Pole right there. That little stick. And just a quick story. So people pay a fortune to come, rich people, not like us, pay a fortune to come into South Pole, and they get off, spend 20 minutes, jump over to what they call the ceremonial pole with all the flags, get their picture taken, and they never walk, another 30 or 40 feet to see this. And the ice here moves 10 meters a year. So every year the USGS comes in and resurveys the location of the South Pole because it's tied to the continent underneath, not to the ice that's sliding over the continent. What I want to point out too is, let me just go back, is you might not see it, but this is a tall derrick. This was the drilling operation that we used in 1982 to collect an ice core to 300 meters, not a very long ice core. Just keep that infrastructure in mind because toward the end I'll show you the infrastructure we use now, much, much better. So Lonnie's first drilling in the tropics was on a place called the Quelccaya ice cap. This is Lonnie right here as a young man with his team. And this was the first successful drilling to bedrock on a tropical glacier. And it took us 5 years to get this project going because we tried to do the project using the infrastructure, the drills, etc., that we'd been using in Antarctica, and we found that it was impossible to get it up to 18,600 feet in the southern Andes of Peru. So we ended up building the first solar-powered drill using these 48 solar panels. How do we get to the other glaciers? Well, we use helicopters. This is in Alaska. We have a single-engine aircraft that we used, and we use the helicopter to sling load a lot of our gear. The Bruce Plateau, where my team drilled in 2010, we used the ski-equipped Twin Otter. And here's another place I've been in Antarctica, Seipel Station, named for Paul Seipel, who was the Boy Scout who went to Antarctica with Admiral Byrd. And this is the close-up showing, you can see the skis here, on this C-130. This is what has given the U.S. the advantage of working anywhere in Antarctica. None of the other countries working in Antarctica have these ski-equipped aircraft. If we're working in Tibet, then we use trucks, and the trucks often get stuck. So this is a common occurrence here. For the Quelccaya ice cap, in the early days, we had to use horses. And in northeastern Tibet, man-hauling. So ice cores Ice cores are very powerful contributors to multi-proxy reconstructions. It's important to remember that we've got other systems that provide proxy histories. I talked about those or showed you examples. Ocean cores, lake cores, speleothems, etc. There's no single best proxy indicator. Every proxy indicator records about its environment pretty locally, unless it's a gas in the atmosphere that is globally mixed, and we'll look at that in just a minute. So I'm showing you the two, I would say, endpoints for ice cores. So on the left is a photograph of an ice core from the Gallia ice cap in northwestern Tibet. And you see a dust layer and then the fairly clean snow and the dust layer. This is an annual layer. And because there's a monsoonal climate there, most of the snow comes in one season, then it's dry, and you get a dust layer. And what's nice is that you can actually count these back in time. It really helps you when you're preparing a time scale for your core, or putting a time scale on the core. This is what a typical polar core would look like. You don't really see anything at all, and yet there's a tremendous amount of information that comes from the polar cores. So, for example, we use the oxygen and hydrogen isotopic ratio as a proxy for temperature. We can measure the chemistry of the ice, and that reflects the chemistry of the atmosphere. Net accumulation, we can determine how much snow fell in a given year, again, by the thickness of these layers. The dustiness of the atmosphere. We can now look at the chemical composition of the dust and determine something about the paleo winds, the winds that brought the dust from its source to the deposition site. We also can extract pollen from ice cores in the lower latitudes. We don't get pollen in the polar regions. That tells us about vegetation changes. We have certain species like sulfate, aerosols, tell us about Earth's volcanic history, and also anthropogenic emissions. And I'll show you some examples of these. But I want to show you probably the single most important, up to date to now, science is always changing, but the most important record that's come forth has been the record of the gases that are trapped in the bubbles in the polar ice sheets. So here's a photograph. This is actually a photograph I took on the Bruce Plateau, just because it's a great shot showing the bubbles in the ice. This thin section also shows bubbles, but you probably can't see it from back there. Now, in the graph, this is today, going back 800,000 years. To date, this is the oldest ice core that's been collected anywhere. And so we have a temperature here, which is based upon the oxygen and hydrogen isotopic ratios. And today, the Holocene, it's relatively warm. The last interglacial, or the last glacial, the previous interglacial called the Eemian, another glacial, and you can count them, the glacial interglacial stages. And then in blue is the carbon dioxide concentration from the bubbles in this core from Vostok, or this is from Dome C. The Vostok record only went back 400,000. Now the drilling at Dome C has taken that back 800,000 years. In blue is the CO2. So typically, if we just stand back and look, you can see that when the Earth is warm, we tend to have higher concentrations of CO2. When we're in a glacial stage, the CO2 concentration drops by about 100 parts per million. The important thing to see here is that during these interglacials, or these warmer periods, the CO2 doesn't rise above 300 parts per million, and we typically use the value of 280 parts per million as the pre-anthropogenic concentration during warm periods. And during the glacial, or the glacial stages, CO2 drops to about 180 to 200 parts per million. And this is very important because it allows us to put in perspective the concentrations today. 405 parts per million is the concentration today. And you can see that at no time in the last 800,000 years have we had CO2 levels as high as they are. And in fact, to see CO2 levels this high, we have to go back about 3 million years in Earth history. Also, want to point out that the IPC greenhouse gas emissions scenarios suggest that under business as usual, meaning that we don't take measures to reduce emissions and emit as we are today, that the concentration will likely be somewhere in the range of 1,000 parts per million. The important thing to remember is that CO2 remains in the atmosphere for a long time, unlike methane that has a residence time of maybe 10 to 14 years. So this is why we see so much conversation about CO2. And if we look at the decay curve for CO2 in the atmosphere at 100% at time zero, at 100 years in the future, about a third of the CO2 that we emit today will still be in the atmosphere. And 1,000 years from now, 20% of the CO2 emitted today will still be in the atmosphere. So this is a real challenging problem for us because it's not something that will be easily solved. And currently we're not on a path. We're not where we should be on the path to reducing our emissions. So just back to some of the other information that the ice cores can provide. We can look at the concentrations from multiple or 5. These are 5 cores that I've drilled in Greenland. We've composited these, and we're looking at the excess sulfate concentrations, non-volcanic excess sulfate. We can remove the sulfate from other sources, this is 1800 to 2000, and you can see the increased coal burning that began at the beginning of the 20th century. And I like to show this because I kind of consider it a good news, bad news, good news image. The sulfate is climbing, but in 1963, with the enactment of the Clean Air Act and then strengthening of the Clean Air Act, you notice that right around 1970, the sulfate concentrations over Greenland have begun to diminish. And the sulfate here is coming from either the North American continent or from Western Europe. But we can also measure nitrate in the ice cores. And what we see here is the post-1950 increase in the use of fertilizer. We had the Green Revolution. And also the increase in the number of vehicles. The internal combustion engine produces nitrogen gas. We get the nitrogen oxide, and then ultimately the nitrate. And again, this is the Greenland ice sheet, and this nitrate is coming from the U.S. on this side and Western Europe over here. Now, these are the places that our team has drilled ice cores around the world. So you can see that we have worked extensively in Antarctica, in the South American Andes. The only cores ever drilled on Kilimanjaro were drilled by our team. Over the Tibetan Plateau, the Russian Arctic, Greenland, Alaska, and very recently in New Guinea. I'll come back to that. So in order to do the work that we do, we have to have facilities. We measure the dust. The major anions and cations and the black carbon are measured in this Class 100 clean room here. We also have 2 Picaro cavity ring down systems that do both hydrogen and oxygen isotopic. They measure the isotopes of both oxygen and hydrogen, then we create the ratio. Because we have all these cores, we have to have freezers for storage. We have 2 large rooms. In our storage facility, it runs at minus 30 Fahrenheit, and we have 7,000 1-meter-long sections of core in storage. And our freezer, which you see here on the back of our building, is full. We also design and build our drilling equipment. It's very specialized. It has to be lightweight. As you'll see, many of the equipment has to be transportable by horse or by yak or by porter. And so we have to have a machine shop where we build our drills. So I don't have time to take you to every place where our team has worked, but I've picked out a few examples. Now I want to highlight the Quelccaya ice cap. Is a unique tropical ice cap, largest ice cap in the tropics. It's in the southern part of Peru in the Cordillera Vilcanota. This is the Quelccaya ice cap in the distance. Notice that this is a road. They put in a hydroelectric power plant, which now allows our team to drive to within an 8-hour walk into the ice field. When up until they put that in, it was a 3-day walk into the ice field. This is the Quelccaya ice cap as Lonnie took this photograph in 1977. This is what made it so intriguing. Not only was it a large ice cap, which is the best thing for ice core drilling, you want to drill on like an ice dome, where the ice flow is very simple and so that the ice at depth doesn't become contorted, because all it takes is any overturning of the ice, then you've lost the integrity of your record. These are annual layers. That's what makes Quelccaya so wonderful. The region has a monsoonal climate with about 80% of the precipitation coming in the wet season, and then it has a dry season. So we have the snow, and then we have these dust, little melt layers that contain dust. So this is the wet-dry cycle. Because Quelccaya was so unique, and we drilled that to bedrock in 1983, we essentially, after we published 3 papers in Science, almost like boom, 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 because nobody had really drilled tropical glaciers before and created these types of records, everybody wanted to get samples of the Quelccaya core, just like the Gallia core I'll tell you about shortly. So what has happened is that the technologies and the questions that we're asking have become so much more sophisticated and advanced that we essentially ran out of ice to provide to people who are asking better questions than we asked back then and have much better equipment than we had at that time. So NSF funded us to go back in 2003 and re-drill the Quelccaya ice cap. And here's an example of some freshly drilled core. And if you look carefully, you can see some of those dusty layers. Now, how do you date the core? For a place like Quelccaya, where we've got that beautiful seasonal signal, we can count the dust layers visibly in the core, but we also look at the seasonal cycles in the oxygen isotopic ratio. So we've got essentially our summer, winter, summer, winter, summer, winter, just counting them back. And also because of the monsoonal climate and the dust layers, we've got these annual layers and dust. And this is a section of the core at around 1800 right here. But if we go further down in the core to, say, around 1550, you can see that we're still counting the annual layers in both isotopes and dust. So we can actually create an annually resolved record. The other thing that's so interesting here is how reproducible the records are. These are the decadal averages over the last 1,000 years from the Quelccaya ice cap, or from the Quelccaya core drilled in 1983, and then the 2 cores, one on the North Dome, one on the Summit Dome, that were drilled in 2003. And the main features have remained the same. This little ice age cooling, the warmth here in what's called the medieval climate anomaly. And what's interesting is that how it's been warmer in the 20th century. And in a minute, let me go to it. Now let's look at the precipitation. This would essentially be the thicknesses of those annual layers. And so what we see here is the annual layer thicknesses also match really well between the 1983 and the 2003 cores. So the little ice age cool period here, the early part of it was moist, wet, and the latter part was dry. And also during the medieval climate anomaly, you can see how dry it was. And what's interesting is precipitation has increased in the 20th century. And I'm going to show you that Quelccaya is an ice cap that is shrinking. And it is actually no longer preserving the seasonal variations in isotopes that I showed you at the surface. One of the nice things working in this area is that there are histories of earlier cultures. And so I wanted to point out that Harvey Wise, sitting right here, just had a book published called Mega Drought and Collapse that he's been working on quite a while. We were talking about how hard it is to get all the authors of the chapters to get their chapters in, and Lonnie and one of his colleagues have a chapter in Harvey's book. And this is a little different from the image that I think is in their chapter, but I think what has captured people's attention with regard to Quelccaya is its link to the earlier cultures. And We'll walk through this in just a second, but these prehistoric Andean cultures tended to rise and to fall with the rhythm of climate change, and particularly the change in the water availability. One of the things that is known about the climate in Peru is that on the longer scale, like multi-decadal to century or multi-decadal scale, is that it typically, if it's dry in the coastal areas, it tends to be wetter in the highlands. So you've got an antiphase relationship between the coast and the highlands. Now remember that Kelkaya is recording the climate conditions in the highlands. And so just starting down at the earlier part of the record, say from about 200 to 600 AD, there's evidence of the coastal cultures, not much evidence of the highland cultures, the Mochi in the north and the southern coastal cultures. But as time goes along, now, and at that time, you can see that we had drought in the highlands. But notice now that the highlands are receiving more moisture, and you notice that the diminishment of the coastal cultures, but the rise of the Tiwanaku and the Hori cultures in the highlands. Here, shown here. Now the Kelkaya ice cap shows that medieval climate anomaly, which is also evident in a lake core from Palcacocha Lake in Ecuador. That's here. Then Kelkaya showing the dryness this would be dryness in the highland cultures. And you see the Tiwanaku and Hori diminish, and you notice now the Chimor culture here along the northern coast and the southern coastal cultures back along the coast. Now the Kelkaya ice cap around, 1500 or so, is showing that we have increased accumulation. In other words, it's becoming moist again. We've got more water availability. And that was the rise of the Inca Empire, here, the massive empire, that of course was cut short in 1532 when the Spanish arrived. So you can see that it seems that, these are smart people and they're moving with the water, or in some cases maybe not moving with the water, and then of course the culture collapses. But if we look at the situation today, it's moist again in the highlands and drier along the coast, but where's everybody living? Everybody is living in the coastal area. And that really shows, I like this because I think it points to how maladapted the current situation is in Peru. All the activities are in the coast, but the water is in the highlands. So what's happening to the glaciers? We can use old photographs, but there aren't many of them. This one was taken in the 1930s. This is a ceremony that the people in the area near Cusco every year they would go and have their festival and collect pieces of the ice that they would take home. In 2006, Lonnie and his team were fortunate enough to find exactly the same spot. And if we superimpose the images, you can see how much the ice has changed since the 1930s. That's the 1930 outline. This is the 2006 outline. So everywhere you see the gray, that ice has disappeared. Not only is the ice shrinking, but you'll notice that its thickness is diminishing as well. And this is wonderful, but it's challenging to find these old photographs, and there aren't that many of them. So to look at the modern changes, how things are changing since, say, the 1980s, we have the advantage of using satellite imagery. So this is a Landsat image of the Cordillera Vilcanota here. This is the Kelkaya ice cap. This was taken in 1988. And then this is a Landsat 5 image in 2006. Compliments of Compton Tucker from NASA. Now, if we superimpose, every place that's yellow is no longer glaciated. And if we look at the ratios, we can see the Kelkaya ice cap has lost 17% of its aerial extent, and the Cordillera Vilcanota has lost 24 of its areal extent of ice. I want to point out this right here is the Coriolanus outlet glacier, the largest outlet glacier for Quelccaya. Lonnie took this photo in 1978. This is a very healthy outlet glacier advancing. You'll notice there's not a lake here. It's moving forward, building its terminal moraine. But by 2011, this is the same place. The Coriolanus has now retreated up onto land. This lake covers about 80 acres, and the lake is about 200 feet deep. And we know that because we took a rubber raft and did sounding. This is the margin of the Quelccaya ice cap as it appeared in 1977. Here are two people carrying a drill stem up to drill site up here. Now all of this is gone. All of this is gone, and now there's a lake in this area, a large lake in this area. And this is the margin of the ice cap now. That would be the ice back in here. All this has essentially melted. And in 2002, Lonnie was walking along the margin, and he saw this, it looked like a little marshland, a little wet spot. And upon inspection, it was actually a plant deposit. And so what's happening here is as the glacier is shrinking, it is uncovering plants that it previously overran. Those plants have been protected from the environment for quite a long time. The plant is called Distichia muscoides. This is what the modern plant looks like. This is the Quelccaya plant. And this plant deposit's 5,200 years old. That means 5,200 years ago, the ice was advancing and it overran these plants that were growing here. And at this spot now, I mean, this is a very common plant in the region, but the plant was growing 200 to 400 meters above its modern range. You have to go further down valley now to find the plant. It doesn't grow up around the ice field. Now, let me just point out, I want you to notice the proximity of this person, Lonnie, and the ice wall. This is 2002. This is 3 years later. This is the plant deposit right here, right here. And you can see it's starting to dry up. And you can see how far back the wall is, the ice wall. This is how fast the Quelccaya ice cap is retreating. The important message is that Quelccaya is not unique. Many of the ice fields, particularly at high elevation in the tropics, are experiencing this type of decline. But the plant story is very interesting. We've continued to collect plants. Lonnie was there last year and collected even more plants. But and collecting, closer to the ice margin, those plants' ages are coming in around 6,000 years, 6,300, the average age for 5 plants collected here. And so what's interesting is it took the ice 1,600 years to advance from here to here, and the ice has retreated in 25 years. So what we're seeing, we talk about rapid climate change. This is a rapid climate change. Now, as I said, proxy records pretty much record what's in the local environment. So what our team has been working for over the 40 years is to have a spatially distributed array of ice core records. So when we can, like for example, here are 4 ice cores from the Tibetan Plateau. We can composite the isotopic records for those, and what we can do is do the same thing for 3 records from South America, from the Andes. And we can then look at the regional differences between Tibet and the Andes. So here's the Tibetan oxygen isotope composite, 2,000 is the modern, back 2,000 years. And this is oxygen isotopic ratio. But what you see is we don't see any evidence in Tibet of the Little Ice Age, and we don't really see much evidence of the medieval climate anomaly. So we're able to look at regional differences because in the South American Andes, we have a strong signature of the Little Ice Age, and also of the medieval climate anomaly. But if now we can put these together and we get more of the large-scale change, we have what we call our tropical oxygen isotopic record, or our tropical temperature record. And you can see that, well, you still see a little bit of the Little Ice Age and the medieval climate anomaly, but they're not that prominent. And now the most prominent feature in here is this warming. And if we compare that to the Northern Hemisphere temperature reconstruction, which is in blue, that reconstruction is based upon largely on tree ring records, but also on some on lake sediment records, on glacier, measuring the termini of glaciers. And then in red, we have the meteorological observations. We see the commonality here is actually the warming of the 20th century. It's the biggest signal now. We just had a paper accepted in JGR Atmospheres 2 weeks ago, and essentially the Peruvian ice fields were strongly affected by this most recent 2015-2016 El Nino. In addition, we had the opportunity in 2016 to go back to Huascaran, which is in the north, it's in the Cordillera Blanca in northern Peru, and collect a 10-meter core, and I'll show you that in just a second. Our evidence suggests that Huascaran in the Cordillera Blanca may be the last Peruvian glacier that's currently preserving an unaltered climate record. It seems that the climate records on all these other glaciers are now being affected by the warming that the region is experiencing. The three take-homes from the paper: mid-tropospheric warming in the Peruvian Andes is destroying climate signals preserved in the glaciers and driving glacier retreat. The impact of the 2015-16 El Nino on Quelccaya was more pronounced than any other El Nino event in the last 4 decades. And the Peruvian Andes snow delta oxygen isotopic ratio is linked to Pacific SST sea surface temperatures, regional 500 millibar temperatures, and convection. And if we take a look, we've been fortunate to be able to go back to the Quelccaya ice cap 24 times, starting with Lonnie's very first trip in 1974, when he found the ice field. He only had a photograph of it. They didn't have a map. There were no roads, and it took them the whole season just to find the darn thing. So, but we've had the opportunity to go back. So here, these are the Quelccaya isotope records. You can see in 1976 and 79, this is the upper most recent year, the nice seasonal isotopic signature, and the fact that these are preserved in the core at depth. But by the time we come up to 2003, and more particularly 2003, we still have a seasonal signal in the modern layer, but you can see that the isotopic seasonal variation is now being smoothed. In 2016, at the height of that El Nino, you notice there's no seasonal signal in what we would call the upper annual layer, and you can see how thin the upper annual layer is relative to the prior annual layers. But going north to Huascaran, which is 400 meters higher, we of course had a very nice seasonal signal in the 91 core, but you can see the 2016 10-meter core that they hand drilled still contains that nice isotopic signal. So in about 2 weeks, we're submitting a proposal to go back to Huascaran and re-drill there, again, to capture that record, because it will, as the isotherm, the 0-degree isotherm in the atmosphere rises, as it will in the future if warming continues, it won't be too long before the record on Huascaran will not be preserved any longer. And there's only one core from Huascaran, the one we drilled in 91, and it's in such demand. The record goes back 18,000 years. And it's in such demand for new techniques, et cetera, we can't provide the ice, so we actually need more ice. So ice physically responds to climate change. It's an indicator of climate change. This is Quelccaya in 1977, you've seen that. Returning to the same spot, Lonnie took this photograph in 2002, That's how the margin has changed. So there's a book called A World Without Ice by Henry Pollock, and it points out that nature's best thermometer and perhaps its most sensitive and unambiguous indicator of climate change might be ice. And in the book he states, ice asks no questions, presents no arguments, reads no newspapers, listens to no debates, not burdened by ideology, and carries no political baggage. As it changes from solid to liquid, it just melts. Ice just shows what the conditions of the environment are. You can't really politicize ice as you can other things. So what's happening to ice around the world? We've got this recent and rapid melting of glaciers around the world. This shows the change in the mean glacier length since 1700 at many places around the Alps, the southern hemisphere, Asia, etc., the cumulative decrease in global glacier ice. These are composites from lots of observations, but we can look at more specifically at certain places. The Greenland ice sheet now experiences summer melt higher and higher, at higher and higher elevations. And this is a photo that I took riding up to one of the drill sites in Greenland, and we work there only in the summer. You can see the melt lakes right here. And what happens is, you get more melting, and then you get these little rivers of ice, or rivers of the water, and the water then runs into these crevasses that are called moulins. And the schematic shows that, if you have a lake, and it actually can build this moulin or conduit into which water can actually reach the base, lubricate the base, and then the ice slides more easily. The other thing is the surface is warmer than the ice, obviously, and this surface water is warmer, so it's a very effective way to transport heat into the ice sheet. The Antarctic ice sheet is also warming. The continent as a whole is warming about 0.1 degrees centigrade per decade over the 1957 to 2006 period. But you'll notice that the West Antarctic ice sheet is warming much more. The East Antarctic ice sheet is very stable. It's grounded on bedrock that is above sea level. But the West Antarctic ice sheet is relatively unstable. It's called a marine-based ice sheet, and it means that the ice bedrock contact is suppressed below sea level. It makes it very, very susceptible to disintegration. The East Antarctic ice sheet has about 60 meters of water equivalent. If all the water, the floating ice does not contribute to sea level rise. That's important to remember. It's only the land-based ice that makes its way to the ocean that raises sea level. This is very stable, and we don't think about it too much. The West Antarctic ice sheet contains about 5 to 6 meters of sea level rise equivalent, and there's much concern. And the Antarctic Peninsula is one of the places where on the Earth where temperatures are rising most strongly. And just to give you an example, this is a project we had in 2010 to drill ice cores, an ice core to bedrock on the Bruce Plateau in the peninsula. This is our drill site. This is our skiway. We used a twin otter equipped with skis. 6 of us went in, set up this camp. We spent 42 days there. We drilled 448 meters to bedrock. This is what the freshly drilled ice core looks like. But I wanted to point this out and bring your mind back to that big drill setup that I showed you in Antarctica in 1982. Under this dome is everything we need to drill the cores, process the cores, and store the cores. Because we've been able to really slim down our equipment, slim down the number of people. Only 6 people is what it took to do that job. Whoops. Just to show you, the conditions here were relatively harsh. We had lots of high winds, low visibility. Then we had drifting snow. Structures got quickly buried. Constantly, this is my sleeping tent. You can see constantly there's the shovel, constantly having to landscape. And just point out here, in 20 minutes the conditions could change. We're looking out the flap of the drill tent down to our sleeping tents, and in 20 minutes it could look like that. So it was a very interesting place to work. We just had a paper published last year in JGR Atmospheres, in which we've reported that we found that the accumulation on the Bruce Plateau provides a nice proxy for the extent of sea ice in the Bellingshausen Sea. A lot of concern about what's happening to sea ice, both in the Arctic and the Antarctic, but the only records that we really have start in 1979 with the advent of satellite-borne sensors. So if we can use these proxy records to reconstruct the sea ice extent, then that's going to be very helpful to know how unique what we're observing today with sea ice, the diminishment of sea ice is. And the key points there were that the ice core-derived accumulation from the Antarctic Peninsula preserves a signal of Bellingshausen sea ice extent. Accumulation and sea ice extent respond similarly to large-scale climate oscillations. You might not study these, but such as the Southern Annular Mode, the El Nino Southern Oscillation, and the Trans-Pacific Index. And recent trends of increased accumulation and decreased Bellingshausen sea ice extent are unique in the 20th century. So we were able to show that this decline of sea ice in the Bellingshausen since 2000 is unique. They've not seen like the decade that we just saw over the entire 20th century. The West Antarctic ice sheet, I mentioned a lot of concern, particularly in this area called the Pine Island Embayment. 2 papers came out in 2014 talking about the irreversible state of decline of essentially the discharge of ice from the Thwaites Glacier and from the Pine Island Glacier into this embayment. And the concern is that at some point the ice in these ice streams could essentially start draining more of the ice up here in the Bentley subglacial trough, and that will raise sea level. Global sea level is rising. You can see early in the 20th century the rate was about 1 millimeter. In the middle of the 20th century, about 2 millimeters a year. And now the best measurements come from the satellites, 3.1 millimeters a year up to 2012. And today, sea level's rising at 3.3 millimeters a year. In the early part of the record here, the primary driver for sea level rise was the thermal expansion of water. 70% of the planet's covered by water. We've looked at what's happened with the globally average temperature over this period. And so if you heat water, it expands. The ocean basin isn't getting bigger, so the sea level has to rise. That was thermal expansion. And then the alpine glaciers started kicking in, and now we've got the ice sheet starting to discharge. We have other changes going on in the Arctic. This is the minimum Arctic sea ice extent. A lot of concern here as to at what point in the future might we have an ice-free Arctic Ocean. Right now, it's even of concern. This is 2017. The lowest minimum was in 2012. But you can see that they can now circumnavigate the Arctic in the summer. So we're going to start seeing cargo ships taking cargo from Europe over to Asia. We're going to see cruise ships. Oil and gas exploration will undoubtedly get underway very quickly in here. So there's a lot of concern as to what's going to happen in the Arctic and the development there. Running over to Kilimanjaro, the ice on Kilimanjaro is, you've heard that about the diminishment. This photo shows the ice extent on the mountain, draping over the mountain in 1912 down to 2006. We drilled 6 ice cores to bedrock on the 3 remaining ice fields on Kilimanjaro in 2000. We've been mapping the retreat of the ice on Kilimanjaro. This map's, don't try to read it, but essentially 88% of the ice cover that was present in 1912, that's this outer line, had disappeared. by 2000 when our team drilled, and 40% of the ice cover that was present in 2000 when our team drilled has disappeared. This is the northern ice field. We collected 3 ice cores from the northern ice field. The record goes back 11,600 years. The northern ice field has been present on Kilimanjaro for over 11,000 years, and in just 1 century, we've already seen the diminishment underway, and it's very likely that within a few decades, the ice fields, all 3 of them, one is gone. The remaining 2 ice fields, the Furtwängler Glacier and the northern ice field, will probably be gone within a decade or 2. And this is the Furtwängler Glacier, where we drilled 1 core to bedrock. It's now broken into parts, small parts. The only ice fields between the Andes of Peru and the Himalaya are in New Guinea. New Guinea actually, there's Papua New Guinea and Papua, Indonesia, and the ice fields we drilled were in Papua, Indonesia. As they appeared in 1936, 1991, and 2001. This is our team, our setup, drilling on the east north wall fern what was I going to say? Anyway, I was going to say something, forgot that. Here's our drill tent. Again, now notice it's even getting smaller. The drills are getting smaller. But, if you're going to go to a place like this, you have to have light equipment. If we look at the maps that have been made of the glaciers, both on Kilimanjaro, shown in red, this is the aerial extent in square kilometers, in red for Kilimanjaro and black for Indonesia, you can see that they're both declining, and probably around 2020 or so, both may be gone. Now this, I'm going to show you, this is where we drilled in Indonesia, or in Papua, and the camp was here, and then people would walk up here to drill. Now, this is 2010. We've taken repeat photographs. This is 2012. You want to look in this area. 2014, and then in 2016. These 2 ice fields are now totally separated. So that's how fast these glaciers are going. And the last place I want to go to is what we call the third pole. This would be to Tibet. It is just like the polar regions. It's high, it's dry, it's cold, and it's affected or threatened by climate change. So it's centered on Tibet, the Tibetan Plateau, and the Himalaya. It covers 5 million square kilometers. It's one of the largest glacial stores of fresh water. It's often called Asia's water towers. Now I have on here the major rivers. You can see the Indus River here, the Ganges River here, and the Brahmaputra River here. And these glaciers feed these largest rivers and help sustain 1.5 billion people in 10 countries. So what's happening to the glaciers here? We can look at photographs, the Keytrack Glacier, 1921 to 2009, but I want to show you what the ice core records can tell us about the retreat of these glaciers. This is a place in the western part of the Himalaya called Gurlamundata, and atop is a glacier called Nanunami Glacier. It's not a trivial ice mass. This is the Nanunami Glacier. This is our drill site out here. Here's a person walking out from the camp on the margin out to the drill camp. We recovered 3 ice cores to bedrock in 2006 at those depths. Just to show you how the ice gets from the ice field down, we have special backpacks that the Sherpas use to carry 3 1-meter core tubes, and they walk down to the edge of the ice where we have yaks waiting, and the yak herders, are there with their yaks, and we have our core boxes positioned. We have 6 meters of core in each box, so it's 12 meters to a yak, and we drilled over 500 meters of ice. So now we need a yak train. You can see all the yaks. And yaks are like cats. If you've ever tried to herd cats, it's challenging. And you've got to have your yak herders, and their yaks are very important. The yaks take the ice cores down into the bottom of the mountain here, where we have trucks with freezers on them positioned, and then it takes 2 days to drive to Lhasa, where we put the ice in freezers. It's a fully collaborative project with our Chinese colleagues, so we split the cores in Lhasa. The Chinese colleagues have half of the cores, we have the other half. They go to Beijing, then to Chicago, and then to Columbus. And it's a miracle they make it frozen, but they do. But I want to I'm wrapping up now. I only have about 4 more slides. But one of the things when we drill an ice core, one of the things that we do is, the first thing we have to do is create a time scale. And we look for these beta radioactivity horizons. These essentially are the remnants of thermonuclear testing. So in the 1962 and 63, the Soviets had atmospheric detonations that released strontium and cesium into the atmosphere. These tests were in the South Pacific, and they blanketed Asia. And so here, this is 4 of the glaciers that we've drilled in Tibet: Dunda, Galia, Dasapu, Piragangri, and Nanunami. And you can see the 1962 beta peak in all the cores, but not in Nanunami. What that means is the ice that was deposited in 1962 on all these other glaciers and was deposited on Nanunami has melted and it's gone. There's no 1962 horizon. The other horizon that we look for is the chlorine-36 from the Ivy tests. This would be a detonation at sea level and produces chlorine-36 that goes around the world. Here's China, Kilimanjaro, Peru, Greenland, and the Swiss Alps. They all have the Ivy test, but not Nanunami. That tells you that the ice that was deposited between 1952 and 1960, when those detonations were going on, no longer exists on Nanunami. That record is history. It's gone. And this is what's happening with ice in Tibet and the Himalaya. The greatest decline, the circles tell you the rate of the area change in percent per year. So the bigger circles you see in the Himalaya,